When we're looking at second order kinetics, which follow the general rate law Ka squared, we can integrate that one as well. In doing so, we get a very useful formula, which we can use just like we could for the first order. We have 1 over, so we have the inverse of our concentration equals positive Kt plus 1 over our initial concentration. Graphically speaking, if we were to graph concentration versus time, natural log of concentration versus time, and then inverse over time, we're going to see that we're going to end up with exponential functions for the first two, but a linear graph for our 1 over, our inverse. That tells us this follows second order kinetics. You'll see this pattern of graphs if your particular reactant is second order. And just like before, we can use this to determine the concentration at a given time, given our starting concentration. And so let's take our same example from before. We can say, okay, well, at 510 degrees Celsius, we're going to say that A turns into B, and again, we're going to say it's now second order, because why not? We can have fun with it. At time 0, the pressure is 135 torr. What is P at 1420 seconds? And K was, let's scroll up and use the same values because I'm lazy, negative 6.8 times 10 to the 4, negative 4. Okay, so if we go ahead and do this, we just need to write down our formula again. 1 over concentration of A at time t, which is what we're solving for, or rather we want the opposite of it, right? Is going to be equal to Kt plus the 1 over our initial concentration, or pressure. Again, either one works here. So that's going to equal 6.8 times 10 to the negative 4 times 1420 plus 1 over 135. Bust it out. So 6.8 times 10 to the negative 4 times 1420 plus 1 over 135. We get 0.973, and that's our inverted value. So we just need to do the inverse of this. So if we raise this to the negative 1 power, we're going to get AT, our concentration. So 1 over our answer, we get 1.02, I guess 3 with proper rounding, and so that would be our answer here. So in this case, we have very little pressure left, because in second order, we tend to see things depleting faster, right? Because it's related to the square of the concentration, so we have very little pressure left at the end here. But the way of solving it is essentially the same, just plug in stuff. So K, T, and your initial concentration. Just make sure you use your calculator. In this case, we're doing the inverse. Last time we had to do the exponent function, we had to do e to the x. This time we do answer to the negative 1 power, x to the minus 1 power on your calculator. So that's generally the opposite. There's usually an inverse button on your calculator, but you can just raise it to the negative 1 power. All right, so we got our value here. Again, if we're going to look at the graphs, for a second order process, for something second order, we're looking at the inverse reaction to be linear. But the natural log and the regular concentration should both be exponential. But again, we see the same kind of y equals mx plus b type formula here. So for second order kinetics, that's our formula.